We now want to talk about electric field. So first we fix a charge capital Q and we want to find electric field associated with this charge capital Q. And we also have a very small charge, infinitesimal small charge, and this charge is conventionally taken to be a positive charge Q. This is called a test charge. So you have a charge capital Q whose electric field you want to find, and you have a test charge. So electric field due to a charge capital Q at a point in a space is the force that a test charge would experience if placed at that point. So we have a charge capital Q and we have this test charge which you place at certain point where you want to find the electric field. So the distance of the test charge from the charge capital Q is r vector, or distance is just r. So notice that this is small q, the test charge experiences the force. So the force is given as K times capital Q times small q divided by the distance between them, r square times r hat. So the electric field associated is K times Q divided by r square times r hat. So notice that I have dropped the test charge from the force. So electric field is equal to force times the charge. Now let us talk about a system of charges. So say you have a system of charges. In that case, we use principle of superposition to find the electric field. So just like the force, now we are trying to find the electric field generated by a bunch of charges. So you have Q1, Q2, Q3, Q4, all these are charges. So the electric field would be again K times capital Q1 divided by R1 square times R1 hat. So that is the position of the test charge compared to charge Q1. Then E2 is K times Q2 over R2 square times R2 hat. Now again this R2 vector would denote the position of the test charge compared to Q2. E3 you have K times Q3 over R3 square times R3 hat. Again this is the position of the test charge compared to Q3. And finally you will talk about position of the test charge compared to Q4, and then you have electric field there. K times Q4 divided by R4 square times R4 hat. So this is our test charge. So this is R4 vector. From Q3 the position of the test charge is R3 vector. Then here you have R2 vector, and from Q1 you have R1 vector. So you keep varying this charge Q, you keep on putting it at different places and you keep finding the value of the electric field there. So say you can put test charge here or here or here or here, and accordingly R1 vector, R2 vector, R3 vector and R4 vector will change, and therefore you will get a different value of the field for each of the charges. So the total field would be now the sum of these fields. So E vector would be E1 vector plus E2 vector plus E3 vector plus E4 vector. For n charges, we can repeat this situation, and instead of q1, q2, q3, q4, we can just go on till qn. And then the total field would be the sum of individual fields. So the total field E vector would be I equals to 1 to n, and then you have individual fields associated. So individual fields will be k times capital Qi divided by Ri square times the associated unit vector. Now let us do an example about this electric field, and this example will relate electric field and the force. So say you have this charged pendulum and it is carrying a charge q. So this pendulum has some weight, it has a charge, and it is suspended in the field. So pendulum has charge, a mass m, and is suspended in the field with some strength. Yeah. So say the strength of the field is E. So say the string of the pendulum makes an angle theta with the horizontal. So you can see the weight mg is acting downwards. The force, the electric force, is keeping it in equilibrium, is acting away from the wall. So in equilibrium you have T sine theta is equal to mg and T cos theta is equal to force. So force is equal to Q times E. So that is the formula relating electric field and the charge. So this implies tan theta is that the T sine theta over T cos theta is equal to mg over QE. So this is the equation at the equilibrium.